Okay, so here we want to compute the integral from -2 to 2 of 1 over the square root of 4 minus x squared dx. So the first thing I notice is that this function here is an even function. In other words, if I plug negative x in, everything would still be the same, right? And that means that this thing has symmetry about the y-axis. In other words, this graph, whatever its graph is, will be a mirror image about the y-axis. And that's a powerful thing to observe because it's going to make the work that we need to do here for this problem, it's going to make it actually a lot nicer, because instead of having to look at the integral from -2 to 0 plus the integral from 0 to 2, look at two separate integrals, because I can recognize this thing is an even function, it's a mirror image about the y-axis, then I can just look at the integral from 0 to 2 and double it. And that's actually exactly what I'm going to do, is say that I just have to do it halfway. And then I only have to deal with the one asymptote. So this is going to be twice the integral from 0 to 2 of dx over the square root of 4 minus x squared. So we have to work that one out. And here's what we recognize here about this thing. I'm going to leave that 2 just kind of hanging around. He's just going to kind of hang around, and I see I have a 4 minus x squared. In other words, I have a squared minus x squared, or a squared minus u squared. Right? Remember, we integrate those by doing our substitution. Right? By doing our substitution, which would be, in this case, x equals a sine of theta. So a is 2, since it's a 4. So x equals 2 sine theta. And dx will call for a derivative of that, which would be 2 cosine theta, d theta. Okay, so we can make that change. So we still have the 2 out front. I'm not going to worry about my limits of integration for a little while. Okay, I'm going to forget about my limits of integration for a little while. Actually, let me say it this way. I don't want to say equals here. I'm just going to leave that 2. He'll come back in later. Forget about him for the moment. But later on, we'll come back to it. So I'm just going to do it this way. Drop off the limits of integration. So I don't have to worry about writing those out right now. We could do that, but I just don't want to bother. Okay, so I'm just going to work on the inside part here, and we'll come back to the integral part from 0 to 2 and the 2 times of it later on. So this will be dx becomes 2 cosine theta d theta, 2 cosine theta d theta over the square root of 4 minus 4 sine squared theta. But the 4 minus 4 sine squared theta, the 4 would factor out. The square root of that 4 would be a 2. And then you'd have 1 minus sine squared. Well, 1 minus sine squared is cosine squared. Square root of cosine squared is just cosine. So we actually have a 2 cosine theta there in the bottom to cross out with the 2 cosine theta in the top, leaving us just with the integral of d theta, which is just theta plus a constant. But since x equals 2 sine theta, that means x over 2 equals sine theta. Then that means that theta is the arcsine of x over 2 plus a constant. And now we can go back to our original problem here. All right, and remember that at 2 this thing is undefined. So our problem would be to limit as b approaches 2 from underneath, right, we're taking on values smaller than 2, of 2 arc sine x over 2, evaluate it between 0 and b. Okay, and we start to work that out. Okay. So limit as b approaches 2 from the left of 2 arc sine of b over 2 minus 2 times the arc sine of 0. And what do we know? Well, as b approaches 2, arc sine, it's going to be arc sine of 1. What's arc sine of 1? That's actually something we can compute. Arc sine of 1 is just pi over 2. So that's going to be 2 times pi over 2 minus arc sine of 0, which is just 0. So all told, we actually have the overall whole integral of that original function there is actually approaching pi. There. That original function that we had is actually approaching pi. Again, remember, I kept the 2 out for a while, brought it back in when it was integral time. And again, this is the asymptote, so I just did 0 to b with the limit. Okay, so we're going to work that out. We're going to compute those arc sine values, and there we go.